Yeah, hi. Yeah, thank you for the very nice and kind introduction. And also, thanks a lot for Professor Hong, Chamgil Hong's invitation to become a speaker. My name is Yuyin Zhou, and I am currently an assistant professor in U Santa Cruz in the computer science and engineering department. Uh, and I was collaborating with Professor Hong on several medical projects. And today is my great pleasure to introduce our group's recent research that includes visual perception and most importantly, multimodal interaction and reasoning in medicine. And I apologize for the background because it's nighttime here in California. Can everyone see my screen? Okay, great. Okay, so let's start. So today I would like to introduce our group's work stemming from the earliest simple pattern recognition to build medical vision, standalone medical vision systems to the nowadays advanced systems capable of complex clinical reasoning. So specifically, my talk will contain three components. First, we will introduce the background on medical vision and also how to build medical vision models for different medical vision tasks. And secondly, we would like to introduce the generative foundation models in healthcare. I will talk about some recent progress in this aspect and also some of our recent works that uses generative AI to tackle different challenges in healthcare. And finally, I will introduce our recent works towards complex clinical reasoning, especially the reasoning LLMs in medicine. So medical vision in the old days was basically a standalone component. As you can see from many of the previous computer-aided diagnosis systems, there was different models that built for example, medical image classification, tumor localization, and segmentation or other different tasks. Now, my group, when I was during my PhD days in the Johns Hopkins University, we built a lot of medical image segmentation models aiming to detect early pancreatic cancer. To resolve this problem, we started by asking, what can AI see in medical images? So we trained the supervised medical image segmentation models using, for instance, in this case, the annotations, pixel-wise annotations from the pancreas, as well as the pancreatic tumor as a supervision. We can get very high quality segmentation models that can segment accurate organ and tumor. So what it gave us is the pixel-wise interpretation of the images that can help us understand where the pancreas lies and also where the tumor lies as a part of the pancreas. Also, this was our previous technical report about the Felix project, which is basically the key project during my PhDs and at Johns Hopkins University, collaborating with the Johns Hopkins Medical Institute. We use a very large-scale pancreatic cancer dataset, consists of different CT images from different phases. And particularly, this is what we get when we are training the segmentation models. So at that time, we were training the segmentation models in two stage. We're trying to mimic what the doctors do in a clinical workflow, which is to first look at this whole image and then to understand where our target of interest lies. And then based on this region of interest, we then zoom in and to further see where the pancreas and the pancreas tumor lies. So by this algorithm, we can see that we can train very high quality segmentation models that can enable us to see very small tumors. Now, these tumors was previously missed by the experts in the Johns Hopkins Medical Institute. But with the help of our segmentation model working as a second reader, we can see now we are able to retrieve this false negative from this image scan. And also in some other applications, very similar results. For example, if you use some efficient object detection algorithm, apply that on the colonoscopy images, as you can see, you can apply it to enable the real-time polyp detection during colonoscopy scan. So this can be very helpful for the doctors to understand the colonoscopy images. Okay, so what about models, right? We have seen a lot of different tasks, applications using different tools. But what about the medical vision models that's underlying behind this task? So to understand this, we must go back to 2015 to understand the beginning of the medical image segmentation model, which is the UNet convolution networks for biomedical image segmentation, this was a Mikhail 2015 paper. And this was actually the beginning of the success of medical image segmentation. And I'm sure many of you have already known this architecture, but just to briefly recap, it's basically using a set of convolution layers and using a UNet U-shaped encoder-decoder architecture to do this segmentation task. So this foundational architecture has inspired a lot of follow-up works. For instance, 2016, the same team from the UNet group, they have extended this to a 3D segmentation algorithm, which is called 3D UNet, and this can help learn the dense volumetric segmentation. Now, further, we from the Johns Hopkins team, together with Professor Alan Yu, which was my PhD advisor, we also developed a fixed point model for pancreas segmentation, specifically for this Felix project. The key idea is also to use the UNet-like architecture, but to do that in the coarse to fine stage, as I have previously mentioned, to first look at the whole images and then zoom into the particular region of interest to look at where the pancreas and the pancreatic tumor lies. And later, 2018, there was actually big breakthroughs. Not a very successful model, which was the NNUNet, self-adapting framework for UNet-based medical image segmentation, which was later published in Nature Methods. So the key innovation from this paper is that they have configured this self-adapting framework where you can easily adapt this to any type of task. For example, like whether it's for CT, for X-ray, for MRI, for ultrasound, for instance, it doesn't matter. And also you can flexibly choose whatever architecture, whatever targets that you aim to segment. You don't need to train or fine tune a specific model for this particular task, but instead you just use the NNUNet because this framework actually allows you to automatically do the data preprocessing based on different tasks and different modalities, and later on even automatically devise a network that is tailored for this specific task. And this architecture was very, very powerful. It achieved a lot of state-of-art, over 20 state-of-art results on different benchmarks. So it was a very popular backbone for medical image segmentation, and it was widely used even until today. And also there are some other architectures, for example, UNet++, which was also a very popular backbone to add additional skip connections in the UNet framework to do the medical image segmentation. So these are all very popular backbones. NNUNet was kind of the state of art and the standard architecture from that point on to do the medical image segmentation. Okay, so basically that was everything before the born of vision transformers. So after vision transformers was proposed in 2021, actually late 2020, immediately we noticed a huge potential stemming from the vision transformers. So in our group, we have proposed a TransUNet architecture, which is the transformers, using the transformers in the UNet backbone. And we find that it can make very strong encoders for medical image segmentation. So this was our paper. And also some follow-up works after our TransUNet is the swing UNet, the UNetter, and the swing UNetter. These are all different variants of combining the very successful vision transformers with the previous successful convolutional-based UNet architecture. So let's look at how our TransUNet is implemented. So specifically, this is the architecture. So as we can see, it's basically still very similar to the previous UNet architecture, consisting of the encoder path as well as a symmetric decoding path. Okay, so for the encoding path, basically there's a series of convolution layer followed by max pooling layers that keeps compressing the image features every time into half of the feature size. And the difference from the previous UNet is that we're now incorporating this transformer-based encoder into the bottleneck of the previous UNet architecture. So, so basically, we insert it after this UNet-based encoder, and then we reshape this feature and upsample it to be integrated in the original decoder. So for the decoder, it's basically still asymmetric to the symmetric to the encoding path. Every time it's upsampled by 2. And finally, we upsample it to the original resolution, same as the original images. So this is going to be our outcome, which is the segmentation mask. So we can see that basically it can improve the performance by a large margin compared to the previous UNet. So it remains till today the state of art for 2D segmentation. And also, as a side note, this was also a top 15 cited 2021 paper in all AI fields. And actually, the top 1 cited paper was the AlphaFold, which already wins the Nobel Prize last year. Okay, so that was our TransUNet architecture. And later on, we also extended it to a 3D framework, which basically is still very similar to the previous TransUNet architecture in the 2D space. We had a CNN-based encoder, a transformer encoder that is going to insert it in the bottleneck of the UNet architecture, followed by a symmetric CNN decoder. Now, the difference is that we're now also integrating a transformer-based decoder to combine with the CNN decoder. So as you can see, the transformer decoder basically it feeds a set of learnable queries and trying to match each query to different class map. So this is basically what we have done. We have thrown in the features from different resolutions, okay, in a decoding path, and we use that as part of the mask coarse attention to try to enable the learning the association between the learnable queries as well as the pixel-wise feature maps. And later on, this was finally decoded into the classification map. Okay, so this was published in 2014, last year, in Medical Image Analysis. Okay, so this was basically a quick review of what medical vision models look like before. Okay, so as I have mentioned, right, since the born of ChatGPT and also a lot of other generative AI techniques, now we are beginning a new era, which is no longer to treat each individual medical vision task as a standalone component in the computer-aided diagnosis system, but now to actually integrate all of them into an integrated medical vision system that is more unified and generalized. So this opens the door for a new paradigm of medical vision models. And actually, the beginning of it is still due to the success of the transformer-based foundation model, which was previously used in the TransUNet as well. But now people find that it can, by using this segment anything model, which is the SAM model, we can also do the same thing in the medical domain as well. So this was published in the segment image in medical images, MedSam paper, which was published in Nature Communications. So this basically opens the door for unified and generalist medical segmentation models. So what it does is that you no longer train a specific, for example, NNUNet or TransUNet on a particular task, for example, like our previous task, to segment the pancreas and pancreas tumors from the CT scans, or to segment the brain tumors from the brain MRI. But now you can do all of the tasks in just one model. So what it does is that it's no longer just taking the input image as the input, but also having a so-called prompt as input. So this is actually a new promptable segmentation. Now, the prompt can be in different formats. It can be even for either the bounding box, the points, or a text description of what you need to find. And then the model will, based on your specific prompt, which specifies your particular task, and based on your current input image, to give you the desired output. So for instance, now we can see that this one model, it can basically do everything in the human body, right? You can treat the abdominal CT scans, brain MRI, even the retina images, colonoscopy images, even pathology images. So you can do all of this just by differentiating the prompts for different tasks. Okay, and also side note, we want to mention that AI not only can see, right? Not only can understand the images by doing different visual perception tasks, but also it can draft text, summarize, and even create new content. So as we can see from many of the general domain tasks, and also I believe in the previous task, the previous talk that talks about the coding LLM, right? AI now can also do some summarization, which is to condense long articles or research papers into key points to create content, writing marketing copies, social media posts, even poetry, to do code generation, to do the translation that break down the language barriers with high quality translation. And the key reason to the success is that now, thanks to the emergence of the generative models, especially large language models, we can see this huge leap in the capability that is driven by these different generative models. So typically, the large language models has become the key unlock. And it is basically now a very flexible tool to use for all different types of tasks, of becoming a generalized tool for basically everyone's daily life now. And the success is that it was trained on massive data that's caught online. So by training on this massive data, we can get this very powerful foundational model that can achieve this different a variety of different tasks. So let's see what it can do in the domain of healthcare. So right now there are a lot of exciting advancements in the medical domain, healthcare domain as well, thanks to the GenAI. Particularly, this Nature Medicine piece shows that adapted large language models can outperform medical experts in the clinical text summarization. So basically, it integrates LLMs into the clinical workflows, and that could alleviate the documentation burden and allow clinicians to focus more on patient care. And also in this piece of work, it shows the feasibility of differential diagnosis based on imaging patterns using a large language model. So specifically, they have tested the well-trained GPT-4 on the general domain, and by assessing this model, they showed that GPT-4 achieved over 90% expert acceptance rate when suggesting a differential diagnosis for radiological image patterns. Also, in this paper, the Gemini paper released by Google DeepMind, they have shown that this is a family of fine-tuned Gemini models for multimodal medical tasks that can analyze 2D, 3D medical images, also generate radiology reports, also answer clinical questions, predict disease risk from the genomic data, et cetera, et cetera. And also, we have seen, thanks to the emergence of large language models, we have also seen generative language AI agents for doctor assistants. For example, this was one piece of work that's called Dex Copilot from the Microsoft. It automates clinical documentation from patient conversations and also can help assist clinicians with daily tasks to reduce the administrative burden and burnout. Okay, so actually following the success of ChatGPT and also a lot of other amazing generative AI, we have also proposed a method for the biomedical domain, which is called Biomed GPT. And this was published last year in Nature Medicine. So this basically shows how generative AI can open the door for generalist models. As you can see from this pipeline, right, we use a very similar to GPT training pipeline to first do the token embedding to generate the embeddings from the text. And also we use another convolution network, which is ResNet, to generate the embeddings from the image patches. We can concatenate the tokens from both the images as well as the text and throw that into a transformer-based encoder, and then followed by another transformer-based decoder this is basically how we train this unified biomedical generative pre-trained transformer. So this pipeline basically opened the door for a lot of different clinical tasks, which is make our pipeline more similar to the clinical workflow. Now, for instance, in the clinical workflow, what the doctors want is to combine different types of modalities, right, and then provide a task-specific prompt. For example, what is our clinical need? Based on that, to generate a text report and also the paired image annotation. Now, our biomed GPT can also do a very similar thing, right? You input a biomedical image and also a paired biomedical test, and then you provided an instruction, which is a prompt here, and then our biomed GPT can, by our encoding and decoding stage, we can finally output the discrete sequences that can enable us to do medical vision question answering, image classification, image captioning, text understanding, and summarization. So this was our results. We have compared with a lot of previous state of arts. Now we tried this on different tasks like the gross captioning, chest X-ray captioning, radiology VQA, image classification, question summarization, pathology VQA, and also a lot of different tasks. And we find that it can achieve better results than the previous state of art in all these different image tags or multimodal task. And also this is our results compared with the previous MedPalm, which was released by Google DeepMind using their own language model, the PaLM model. And we can see that we also show very competitive results and sometimes even better results than the MedPalm model. Here we also show like the performance in different domains. You can see now we can achieve state of art on vision language datasets, object detection datasets, mask image modeling datasets, and also even for some of the datasets that's underbalanced in our data distribution, we can all achieve very competitive results. So this was basically the progress of biomed GPT, and we're now moving to the next stage, which is try to do the same thing just for the medical imaging domain. So previously, the MedSam, right, it can opens the door for a generalist and unified model for medical image segmentation, right? We have shown that it can achieve very good results, very strong results for a variety of different domains, including not just CT, MR, but also pathology, colonoscopy images, even retina images, etc. So now we're thinking, can it do other tasks outside the segmentation task? So here we have shown a pipeline that unifies not just the different segmentation tasks, but also other tasks, including the cross-model synthesis, object detection, in-painting, denoising. So we unify all of these different discriminative tasks as image generation. Now we build a model that is called Medical Vision Generalist, MVG. So as we can see from this pipeline, the idea is simple. You throw a paired input from the image and label, and then based on different, you throw that for training. And then in the testing stage, you input the images, the prompt images and prompt labels to tell your model what to do. For example, what to segment, or to do the detection, or to do the in-painting as the prompt. And then it can give you your desired output. So the methodology actually is very simple. It contains 3 different stages. First, to unify the input and output space. And second, to unify the task. And finally, to do in-context generation. So this is our training pipeline. We have integrated the mask image modeling, which predicts the missing or masked regions in an image based on the surrounding context. We also use the autoregressive training, which is similar to the GPT style training that treats each image along with the prompts, labels, and inputs as a single sequence element, allowing the model to predict the subsequent image based on the preceding ones. So we can see that our results here, we show very, very strong results for different data sets in Word, in BDCV, in AMOS, microsegnet, and also chest X-ray dataset, and also for different tasks, denoising, in-painting, cross-model synthesis, and other tasks, we all show very strong results. Another thing to note is by unifying these different discriminative tasks, we also enable the model to learn more comprehensively from the existing data. So this actually allows us to have very strong scalability. We can see the scalability across different data sets and different tasks. Okay, so that basically wraps up the second part of my talk, which is to talk about Gen AI applications in the healthcare domain. And finally, I want to take a step further to talk about how to build the stronger models towards the complex clinical reasoning. So specifically, I would like to talk about some of our recent works that evaluates and also propose new methods to do the reasoning large language models in the medical domain. So first, due to motivated by the very successful O1 that was released by OpenAI last year, we want to ask whether this extended reasoning paradigm can really improve the medical reasoning. So we provide a preliminary exploration of the O1 preview on different medical scenarios to comprehensively examine three key aspects: understanding, reasoning, and multilinguality. And this is basically our evaluation pipeline, and this is the archive paper from our group. So basically, we throw in different aspects and tasks for the model to evaluate. For example, we choose the concept recognition and text summarization as the understanding task to evaluate knowledge QA, clinical decision support, mathematical and agent task to evaluate the reasoning capability of O1, and also the knowledge QA and agent task to in different languages to test the multilinguality capability of the O1 model. And we use different prompt strategies, for example, direct prompting, chain of thought prompting, which is more advanced prompting, and also few shot prompting. For language models, to understand if O1 really provides additional real benefits, we evaluate not only O1, but also GPT 3.5, GPT-4, Meditron, and Llama 3. So finally, we evaluate on three different aspects, 6 different tasks, 37 data sets using 3 different prompt strategies, 5 large language models. And this is particularly our results. Okay, as you can see, O1 indeed achieves better results across different benchmarks, QA and other benchmarks. And as we can see, this the performance improvement is actually very significant, especially compared to previous Meditron, which is actually a specific medical large language model. So, but also we've been identifying some limitations of the O1 model as well. For example, we can see, So before that, we also want to emphasize that apart from this existing public QA datasets or MCQA datasets, we've also shown very strong results on the new real-world diagnostic QA benchmark. So basically, we curated these 2 benchmarks, Lancet QA and NEJM QA, by ourselves, which are from the quiz questions from the 2 top clinical journals. So as we can see, O1 also achieved the state-of-the-art results on this very clinical challenging dataset as well. However, in the meantime, we also have seen some limitations of this models. I didn't put on the slides here, but we have also seen some limitations. For example, O1 actually has still very large hallucination problem, and also it does not show very strong results on the multilinguality test. So to summarize, we can see some improvement in the complex clinical reasoning, especially in this real-world diagnostic QA benchmarks. We can see the large improvement due to the extended reasoning paradigm. However, the hallucination and other issues still persist using the O1 model. So next, we also want to understand whether this advantage was attributed to knowledge or reasoning, because reasoning models indeed show the boosted performance However, it also has some limitations. And also, we want to understand specifically what contributes to the boosted performance and what needs to be improved. So to understand that, we have performed a study which was recently put out on arXiv called unleashing the potential for the test time scaling paradigm for the medical domain. So this was actually motivated by a previous study that was released by Stanford University called S1, Simple Test Time Scaling. So in that paper, the researchers from Stanford have shown that the SFT, supervised fine-tuning, with just 1K reasoning traces can teach the model how to reason in math and coding. So specifically, these are the results from different math and coding datasets. And they show that just using this very simple test time scaling paradigm, it can achieve very strong results. So what they have hypothesized from the success of the test time scaling is that the pre-trained models already know the necessary knowledge to perform reasoning. So therefore, they only need to increase the token length for reasoning and also use other methodologies like the budget forcing to enforce the model to rethink or self-reflect the results. And these simple methodologies can already, in test time, can already improve the reasoning results because they have already been equipped with very strong knowledge. So we want to know whether the same thing can happen in the medical domain. So specifically, this was in our paper, medical test time scaling. And as we can see, this was the results, for example, for different test time scaling strategies like budget forcing, thinking token control. And as we can see, it's all improving the results by a very large margin. So what about the medical domain? Okay, in the medical domain, we have performed a very similar pipeline to replicate this S1 journey. So first, we do the data curation that basically curates a very high quality 1K sample from the 196K medical QA pairs. We perform the difficulty filtering and to finally generate very high quality 1K samples to do the supervised fine-tuning SFT. And as we can see from these results, in different data sets like Lancet, MedBullets, MedExpert, QA, NEJM, it can consistently improve the results with the increase of the token length. So we can conclude the test time scaling law also exists in the medical domain. However, we also have found several key differences between the medical and the math coding domain. For example, in the math and coding domain, we have mentioned before, using the budget forcing, which is to add additional thinking tokens like weight, for instance, to force the model to rethink, it can largely improve the performance in test time. However, in the medical domain here, what we have seen is that it does not really improve the reasoning quality. And actually, for some data sets or some scenarios, it even lowers the performance. So to understand why this self-reflection does not work, we show this one example. And we can see that even though you enforce the model to rethink by adding additional weight tokens here, because the model was not able to capture accurate knowledge like the math and coding domain, it can actually retrieve some false knowledges from the pre-trained models. And that actually can sometimes even lower the results. For example, like changing the original right results to the wrong results. Or in this case, it's just repeating some wrong knowledge. So therefore, finally, it just still remains to be an incorrect answer. And also, we find that in the medical domain, actually the scale of the COT data matters. Previously, remember in the S1 paper, they have shown that 1K data is already enough. Further improving the scale of the COT data used for self-supervised fine-tuning is not going to improve further increasing the performance. However, in the medical domain, we find that using 23K to do the self-supervised fine-tuning compared using 1K, it actually still increased the performance by a large margin. So this shows that the scale of the COT data matters in the medical domain. So both the previous case and this case shows that the pre-trained model does not capture enough medical specific knowledge to fully unleash the potential of test time scaling. So to increase the performance or to continue to see the scaling law of the test time scaling, we still need to find a way to further improve the knowledge that is stored in the large language models. Okay, so basically this is the conclusion. Same as math and coding, more thinking budget also helps in the medical domain. For example, by increasing the token length, right, we can see the scaling law in the medical domain. However, different to the math coding task, the extent and accuracy of fine-tuning model is still crucial. Okay, so next we would like to ask, right, now we have already answered like what contributes to the improvement, right? In the medical domain, we have shown that accurate knowledge actually matters more. So now we want to see how to fix this knowledge problem, right? Like we have said before, this is going to be a key to further improving the performance of medical large language models. So the first action that we have take is to improve the quality of the COT data. So in one of our recent paper, which is called MedReason, eliciting factual medical reasoning steps in large language models via knowledge graphs, we propose to use the graph knowledge to ground the medical COT. So this is basically a results, a quick snippet of what our MedReason dataset can do. Now the left-hand side, it was the previous generated reasoning traces from the GPT-4o. As you can see, the reasoning traces is not very accurate. It shows early steroid administration seems to be a common yet not strongly effective treatment for ours. So it's a very hesitant and incorrect statement. However, in our case, we have generated much more accurate reasoning traces for this same question. So how to ensure this correctness of the knowledge in this distilled data? We have proposed this MedReason data generation pipeline, which consists of 3 key steps. First, we do medical entity extraction and mapping, which is basically to first decompose the QA pairs into the question set and also the answer set, and also to extract the key entities from the question and answer sets to map that into the different nodes from the knowledge graphs. And second, we use the path searching and pruning. So to find out the paths that can trace the starting point, which is the entities from the question set, to the entities from the answer set. We search different paths and we do the path pruning to reduce the number of paths from the knowledge graph. And finally, the third step is called COT generation and quality filtering. Basically, we are throwing all of those final paths that is retrieved from the second step, and then we throw that into another large language model tool to help us formulate the final COT traces. So this is one case. So from one open source QA pair, so this is a question and answer. So the words in the blue are the keywords, the entity words that can be matched into the entities from those entities in the knowledge graph, and the words in the answer set, which is marked as red, they are corresponding to the final entity from another entity in the knowledge graph. Now, our key goal becomes to trace the paths in this knowledge graph that can trace from the beginning point, which is from the question set, and trace that all the way to the entity in the answer set. And for example, in this case, we can show this many different paths that's marked in the green words, the green entities, and followed by these arrows, we can see many different paths that can start from the start point and also point to the end point, which is the entity from the answer in this QA pair. And finally, after pruning some ineffective or redundant paths, we throw the final path into the GPT-4, and to use that to do the COT generation with the passes. And finally, as we can see in the in the upper right part, this is our final reasoning process that contains reliable chain of thoughts that can form our MedReason dataset. So by perform the supervised fine-tuning SFT on this MedCOT dataset, MedReason COT dataset, we can see that it improves the instruction fine-tuned model more effectively. For example, like this Huatuo COT data, which was yet another COT data that was curated by the Huatuo paper. And this was actually directly created by prompting the GPT-4. So without any grounding from the medical knowledge graphs. And compare with the Huatuo COT dataset with our dataset, we can see that our dataset basically almost improves all of this performance for all of these different benchmarks, especially for those particularly challenging benchmarks that like the MedBullies, MedExperts, MMU Pro. So these are particularly different, challenging datasets. And as we can see, the performance improvement for those challenging clinical datasets, we can actually improve the performance even further. And based on different backbone models from Llama 3 and Mistral Instructor 7B, we can see that our conclusions remain the same. And also, we can see that using our MedReason COT dataset, we can further improve the existing reasoning LLMs. So, for instance, we used the medical COT 8B DeepSeek distilled model, so which are all the reasoning LLMs in the medical domain. We can further improve all of those results. And finally, we want to show a case study here. As we can see, our model, by using the knowledge graph as grounding to generate more reliable COT, now the fine-tuned model actually can induce more accurate reasoning. For example, compared to the previous reasoning process generated by the Huatuo GPT-01 paper, it contains a lot of inaccurate knowledge, like bridge down slanting eyes, for instance. These are all wrong conclusions, knowledge from this clinical scenario. But now in our model, the reasoning results indeed can improve by a lot. We can see that all of those inaccurate knowledge is gone, and actually we now have more effective reasoning path that can tell us how to trace from the question to the answer. So this was one sample from the MedBullets dataset. And more importantly, we want to emphasize that our results are also validated by 7 different specialists. They're licensed clinicians from the Cornell Hospital and also a few more MGH and a few more other hospitals in Korea. So we show that the COT process as well as the generated reasoning from our MedReason 8B model consistently are much more high quality than the previous generated reasoning traces. So that's basically everything about the complex clinical reasoning using reasoning LLMs. And actually, we're now following up with multimodal reasoning. So please stay tuned. We will have more works including multimodal reasoning and also agents that's going to be put out by the end of this year. And finally, I want to take 1 minute. I think I'm probably already over time or about time. I want to take a final minute to talk about my vision of the next frontier in the biomedical domain. I think vision and language are just 2 aspects in the medical domain, and definitely it's not enough to capture everything that a clinician needs to understand a patient profiles. So to understand the real reason for different disease, to forecast the disease progression, and to even prevent some diseases from happening, to enable the preventative care, we need to understand the biological drivers of different diseases and tumor evolution to understand the real mechanisms behind that. So definitely we need to integrate more biological data into this multimodal reasoning and understanding pipeline. So the final goal, I believe, is to build a model towards particularly the creation of unified generative models that synergize clinical imaging and text with diverse biological data, such as molecular, proteomic structures, other proteins, other proteomics, pathology data, and even more modalities such as EHR, etc., to build the intelligent digital twins and enable personalized medicine. So definitely, our next goal in the next few years will be to build more powerful models towards this direction. And finally, I would like to thank all of my previous collaborators and also my wonderful students that I have for the past few years that help us develop a lot of the frameworks that I have shown previously in this work. And also want to thank all of our different support funding agencies from different companies and also from UCSC Hellman. So they have enabled us to do this very wonderful research and also some of my follow-up research. So that basically concludes everything for my today's talk. Thank you for listening, and I'm happy to take any questions.